Am I audible? Can somebody confirm? Am I audible?
Yes, ma'am.
Okay. So I'll share my slides and then we can start. So this is for the tutorial for the week 2. First, we'll do one of the numericals on solidification. Like you might have covered the solidification portion. So this is the numerical. The numerical for solidification, which we'll be solving. So I'll read out the question for you. The question says calculate the size of the critical radius and delta G when gold is formed by homogeneous nucleation. So this question is related to the solidification. So you have to understand that this is related to the atomization process because in powder metallurgy, the atomization is a process where we are trying to melt the molten material, and after melting of the molten material, we are subjecting it to atomization, either gas based or water based, and that results in the formation of the small spherical or irregular type of particles. So here we are dealing with the atomization process, and during atomization, we are developing the small particles of small powders, and these powders are actually formed by the solidification process, in which you might have read about two things. One is the nucleation, and one is the growth of the particle. So first, a powder particle is nucleated from the molten metal, and after nucleation it is converted, it is growing, and it grows to form spherical or irregular particle, um, forms or powders, right? So this is related to atomization, which is having a process of solidification in it. During the process of solidification, there are certain parameters associated with it, which you might have covered, which include the critical radius, and it involves the activation energy. The activation energy for what? The activation energy for forming the spherical particles or irregular particles, for forming the powders, activation energy that is required to form these powders, right? So based on that, we have a question here where we are saying that we have to calculate the size of the critical radius, okay, and delta G naught. Delta G naught is the energy or the activation energy that is required for the formation of this nucleus from the molten metal, right? And it is formed by homogeneous nucleation. So the freezing temperature for gold is 1064. So you can say it is the melting temperature for the gold is 1064 degrees Celsius, and the latent heat of fusion is 1.16 into 10 raised to power 9 joules per meter cube. The solid liquid interfacial energy. The solid liquid interfacial energy means it is the surface energy between the two surfaces as it is nucleated from the melt, because what we have a melt, we have, this is the molten, if this is a molten material, from this molten material we have a nucleus that is nucleated, and that will have a certain solid liquid interfacial energy between this liquid and between this solid that is being formed, right? So we have some interfacial energy between the two, and we have a typical undercooling for homogeneous nucleation, which is having delta T is 230 degrees Celsius. So because you know, whenever we are going for whenever we are uh, solidifying a material, it has associated some undercooling with it. What does undercooling mean? You must have studied this graph, the graph between this delta G versus temperature, and the graph goes like this. this temperature is the melting temperature, right? And here we have solids, we have liquids. So this is the characteristic Gibbs free energy for solids and liquids, where we see that the solids have a lower Gibbs free energy. This is a line for solids, and this is a line for liquids. Okay, so we can say that below this melting temperature, where they are intersecting, below this melting temperature, the solids are stable, and above this melting temperature, the liquids are stable because the delta G value is negative. Below the melting temperature, the delta G for solids is negative. Above this melting point, the delta G for the liquids is uh, negative. So what is this undercooling? This undercooling is this delta G value, the difference between this liquid and the solid. So the delta G value, the undercooling is this value. Okay, because for any solid to be solidified from a liquid melt, it has to go through certain undercooling. We have to decrease its energy by certain magnitude, and by that magnitude, we mean that we have to move below a certain temperature, and that temperature is known as undercooling. So that undercooling is here 230 degrees Celsius. So based on this numerical, you have to find the radius, the critical radius for the particle of the gold that will be formed after nucleation. So you will have to calculate this critical radius. You can take 5 minutes and you can try to solve it. After that, I'll solve it with you. I will also start solving it with you. So, uh, first, here we have we have to first note down that the critical radius, that is the radius at which, what is the critical radius first? The critical radius is a radius at which the surface energies and uh, can you please repeat? I didn't get you. Okay. Because I have to solve it, so this is the maximum size that I can go. If it is clear. Okay, so we have a critical radius. So what is critical radius? The critical radius is a radius at which we have a balance between the two energies. What happens whenever we are having a solidification? This is something that you have might have covered. So a little bit brief before we move further. So we have this. So what we have, if we have a characteristic graph between, this is a graph that we have, this is the energy, the delta G value, and this is the temperature. So when you see this delta G value, it can be positive, it can be negative, right? So there is a balance between the two energies that are happening as the nucleation proceeds. So what happens during nucleation? There is a new surface that is being created, and for creation of the new surfaces we need certain energy. So because there is energy required for creation of a surface during solidification, so we have a value of surface energy that is positive. So this is related to the surface energy, that is the energy of the particle that is being nucleated, the surfaces that are being created. But we also know that during solidification, what happens that as we move, as we try to decrease the temperature, as we have a solidifying temperature, the liquid tries to get converted into solid because of its lower free energy. This lower free energy drives the another energy for nucleation or for overall solidification, and that is known as volume free energy. Okay, so this is the volume energy. So we have two energies that are competing with one another to form the surface or to form a nucleus out of a solid. So this nucleus will be formed only if we have a temperature lower than this melting temperature. If we move lower than this temperature, then only we will have a particle nucleating from a liquid. And second is that we must have certain surfaces being created for the new particle, or particle solidifying. So this balance between the two gives us the total Gibbs free energy. So the total Gibbs free energy is the summation of these two energies, the surface energy and the volume energy, and the balance between the two will help us to find a optimum place where the critical radius will be reached. So what is the critical radius? The critical radius, once you add up these two energies, you will have a curve like this, and this curve is actually telling us that at certain radius, right, at a certain radius, that certain radius is known as critical radius, where the the formation of the nuclei is feasible, and that nuclei will have a tendency to grow into some bigger particles. So for example, this is a critical radius which we are talking about. If we have a radius of the nucleus or radius of the particle from a solid somewhere here, I will write it R1, and I will have a particle somewhere here which is R2, right? So we have two particles, one is R1, one is R2. This R1 is having a radius much less than the critical radius, then much less than what is required for the nucleation and growth of the particles or for solidification. So say for example, we have a particle that has nucleated somehow because of local heating, and it has resulted in the formation of R1, radius of a particle having radius R1. But this R1 is not at the optimal condition, is not at an equilibrium or ideal conditions. So what will it try to do? It will try to decrease its Gibbs free energy. How will it try to decrease its Gibbs free energy? It will decrease its Gibbs free energy, and as a consequence the nucleus will shrink. So there are certain nucleus that might have solidified out of the melt, but after a time these solidified particles again shrink or they get back to the liquid melt because there is not sufficient, they are not at the ideal Gibbs free energy position. Similarly, if we have a radius of R2 that is having a radius greater than what is required for the critical radius, so for this particle also, it has to decrease its Gibbs free energy and achieve an optimal condition. And for that, it will lose its energy and it will try to agglomerate with one another. It will try to coalesce. So these are the two particle radiuses. If it is less than R1, then it will not be sufficient enough to be nucleated from the liquid. If it is greater than R star or greater than critical radius, it will try to agglomerate or it will try to grow into a bigger nucleus, right? So this is a main crux behind this problem, that we are trying to find the critical radius at which the particle will be nucleated and solidified from the melt and it will subsequently grow. So here if you have to find the critical radius, so what we try to do, so first we have to see what is the data that is given in the equation. So we are given that we have a freezing temperature for gold, that is the temperature at which it will melt, right? It is given as 1064 Celsius. So because we have to find, we have to put it in this equation, we will convert it to Kelvin. So it will be 1064 plus 273 Kelvin. So this is the temperature of melting at which,
six answers.
can you repeat?
Around 6 ounce, 6.03 ounce.
I'm not able to get you what you want to say.
The answer will be around R star. The critical is 6 angstrom.
Okay, so you are trying to tell the answer, right? Okay, I'll solve it with you and then you tell me if it is right or wrong. Okay. First, I'll try to solve it for others to see. So we have this melting temperature which is 1064 plus 273. So this is the melting temperature. Now we have also the surface energy. The surface energy value is 1.1, that is 0.132 joules per meter square. And then we have the undercooling, which is the delta T in this equation. So we have surface energy which is given by gamma, which is the 0.132. Then we have the melting temperature which is 1064 plus 273 Kelvin. Then we have this late undercooling which is delta T. So for that will be 230 Kelvin. We can write it like that. And we have delta H. Delta H is the latent heat of fusion. So what we have delta H, I'll write it like this. So that will be 1.16 into 10 raised to power minus 9. Sorry, 9. So we will plug all the values in the equation. So that will be minus times the 2 into the value of gamma surface energy, which is 0.132. Then we have the melting temperature, that is 1064 plus 273. Okay, that will be divided by, because we have this solid interface energy is negative, so it will be negative times. Now we have the value of delta H. The value of delta H will be 1.16 into 10 raised to power minus 9 into the value of undercooling, which is 230 kilocalorie. So this will be your critical radius. So the I think answer is 9.6 multiplied by 10 raised to power minus 9 joules. First we'll try to find this R value, then we'll find this energy value, I think. So that will be 1.32. 1.32 I think it is mm. It will be m 1.32 into 10 raised to power minus 9 meters, right? Because we have to check if all the units are in the same, are of same. Yes, they are same. Joules per meter square, joules per meter square.
So you have to consider 30 in Kelvin.
Where
230.
but it is undercooling. See, it is typical undercooling for homogeneous nucleation delta T. So what is delta T? Delta T is the difference between the two temperatures, T2 minus T1 for example. So that is given by 230 Celsius, which is same as 230 Kelvin because it is the difference between the two temperatures. It is not a single absolute value of the temperature. So the difference will be same whether it is in Kelvin or whether it is in Celsius. Because we are talking about the undercooling, that is the temperature that needs to be decreased for the nucleation of the particle from the melt. So that delta T will be 230 Kelvin or 230 Celsius. So that will be same. There will not be any change of the units. Also, you can check, you can balance, you can see if other units are balancing or not. Say for example, we had the surface energy value. That surface energy is joules per meter square, okay, and that will be multiplied by the Kelvin, and all of this will be divided by the delta H, that is joules per meter cube, right, multiplied by the Kelvin. So the joules and joule will be cancelling out, meter square will cancel out, and then we'll be left with meter as a final unit. Okay, so this is the critical radius of the formation of a gold from a melt, say for example. So now you have to also find the delta G naught. What is delta G? Delta G is the uh, activation energy that is required for the formation of this gold melt from like gold particles from the melt. So this activation energy is calculated from the formula. I think it will be written here somewhere. So I'll just copy the same here for your, so you can see this is the formula for the formation of the activation energy that is required for its formation. So we have delta G naught, that is delta G star, because we are now talking about formation of a nuclei of critical radius from the melt. So we will have a delta G star for the critical condition. So it will be 16 times pi gamma cube, that will be the surface energy, divided by 3 into delta G. What is this delta G? This delta G is the Gibbs free energy for the formation for the volume free energy, which is written here. This is the volume free energy. So this is written here. So we can now convert it to in the form of latent heat, fusion, and temperature. So how is it done? So what we try to do, we take this equation we want to convert this delta GV into, because we do not have any data that is given related to the volume free energy. We have data related to the latent heat of fusion, related to surface energy. So we have to convert this delta G. So how will we do it? We will write for delta G, we can write delta H minus T del H minus T del S, right? Now for the same equation you can write del G is equal to del H minus T, because we know del S is equal to the change in the entropy per unit change in the temperature, right? So we can write it is del S can be written as del H divided by del T. Okay, so we will write del G is equal to del H 1 minus T. This T here is the temperature for the melting divided by del of T. This del of T will be the undercooling. So then finally we have del of G is equal to del of H into del of T. So finally the equation that we will be using to solve will be this. This delta G naught is equal to 16 pi surface energy time 3 times, the melting temperature 2 times, and this. So if we plug in the value, so what will be the value for the Gibbs free energy? This will be 16 pi. This will be 0.132 times 3 times. I mean cube of 0.132. The melting temperature would be 1064 plus 273. You plug in the value for delta H now. The delta H value will be 1.16 into 10 to the power 9 times the square of this, and the undercooling, that is 230 square. So this is the final value for delta G. So can anybody tell me what is the answer for this? Somebody can calculate it. The value of delta G. Just have to plug in these values in the equation. I think if somebody can provide me with the answer, what is the value for delta G star if you have calculated it? Just have to plug in the values. So the answer is 9.67 into 10 to the power minus 19 joules. So this is the amount of energy that is required for the solidification in this equation, in this question. Any doubts? Any question? So this was the critical radius.
Can you please just tell that delta G left hand side what you're
Where exactly? Is this?
uh,
Which one?
yeah, that part little
Okay.
just
Actually, what we have, you might
on the
have.
left hand side again
Okay. So you might have read this equation, which is delta G for a critical radius is 16 pi surface energy 3 times the power raised to power 3 and then 3 delta G. But because we do not have any data related to the volume free energy, we have data related to the latent heat of fusion, we have related to the energy related to undercooling. So we have to convert this delta G, which is present here, into the values of delta H and T, or undercooling, right? So for that, what we do, we write that the delta G, which is a volume free energy, this volume free energy, is given by delta H minus T delta S. This is right. We have studied that delta G will be equal to delta H minus T delta S. So now we can write that delta G is equal to delta S, again the same thing, minus T, but instead of this delta S, we can write that delta S is a function of entropy, is enthalpy. This entropy is a function of enthalpy and temperature. So we write delta T, actually it is absolute temperature, this is not delta T, right? So this delta S will be delta of H divided by the absolute temperature, which is T. Okay. So we have replaced this del S by delta H by T. So now we write delta G is equal to delta H. We take out delta H common in both of the terms because we have delta H, one term. The other term is T delta H by T. Okay. So the delta H will be common in this, and then we have 1 minus T divided by the absolute temperature, which is T naught. Say for example, you can write T naught. I'll just write it here. This will be more clear. So this will be 1 minus T divided by this T naught. Okay. Then we have delta H, this T naught. Then we have one more step here. You can write it like this. That delta G is equal to delta H. Now, because we have 1 minus T naught, so we can write it as T naught minus T, right, divided by T naught. This T naught minus T will be our delta temperature, and this T naught, which we are talking here, is the melting temperature for the critical radius formation. Is it clear? So we are just trying to get the delta G value in terms of delta H and delta T. For that, we are using delta H minus T delta S equation. Then we have delta G in the form of delta H and delta T only. So we have put this delta H with delta T in the equation, and now this is your final equation which you will be using for the calculation. Is it clear?
yeah.
Okay. Okay. So now, if there's no other question, then we can move forward. So based on this was a question based on atomization. So what we have a categorization. Now you can see that for a gas atomization process, we have different types of atomization process, right? We have gas atomization, water atomization, we have centrifugal atomization. And the centrifugal atomization has in turn two types, the rotating electrode type or the rotating disk type. So all of these are the atomization types. And based on the atomization, we can have a range of the particles that are to be formed. For example, for gas, we have a particle range from 15 to 300 micrometer. For water, we have 5 to 800 micrometer range. For a rotating electrode, we have a little higher particle size range, which is 200 to 600 micrometer. And the most important thing is the particle shape. So why we are talking about particle shape? Because Abby said that for a packaging efficiency, for a best packaging efficiency, we need to have a certain type of a packaging, or we need to have a certain type of particle shapes. So for example, for a gas atomization, we will have a rounded spherical particles which will have a maximum packaging in comparison to other forms of particle shapes. While in water atomization, we have a particle shape which is irregular, and for rotating electrode and disk, we have some spherical type of particles. So, based on these particle shapes, we have to decide that which type of atomization we have to go. For example, if we require we are very strictly requiring spherical type of, for example, morphology. So we will not go for rod atomization. So we will either go for gas atomization or we will go for centrifugal type of atomization. But based on the cost, we will choose gas atomization as an ideal approach. So based on our particle shapes, we have to choose the type of the atomization we need to do. Also, it depends on the reactivity of the powders also. So for example, if you have a reactive powder, it will react with water and it can form oxide layers. So if it is undesirable, you should go for the gas atomization. So the identification of which type of atomization needs to be done depends on what is the requirement of your particle shape. It depends on the costing also. It also depends on the uh, type of the powders that you are processing. Are those reactive powders? Are those unreactive powders? Are those noble powders? So all of these factors will decide which type of atomization we have to carry out. So you should remember that what type of shape will be produced in what type of gas atomization. So this is important. So after that, this is one of the morphologies of the produced powders, right? So if we see that there are different types of morphologies of the powders that are produced, I'm showing here. So you have to tell that what is the process that has been utilized for their formation, right? So for example, this is a copper. So you will see a very irregular type of morphology. Or for example, for these steel balls, you are seeing a characteristic spherical type of morphology. For aluminium, you are seeing a spherical morphology. For aluminium, for this type of aluminium, it is irregular. So there are different types of morphologies, and based on the morphologies, because this is very important, because if you do not have an idea from where the powder has been processed, you can check the powder under a SEM micrograph. You can check its SEM, you can check its SEM micrograph, and based on the micrograph, you can decide that which type of processing route might have been used for its fabrication, right? Say for example, we have copper. So what do you think, the copper here, the copper powders that are shown here, by what method are they produced here based on the atomization routes? Can you guess what is the method of atomization that is used for production of these copper?
Water.
For example, for water, so the water was chosen because it is showing an irregular type of a morphology, right? And for iron, what is the type? What is the type of atomization used? Or for either of the steel and the aluminum, can you tell what is the type of atomization used? because the morphology is similar.
Yes.
Gas because it is spherical, right? So what we have for copper, we have used water atomization because the particle size was very irregular. For iron also, we did not see any characteristic particle shapes here, and we could say that it could be produced through water atomization. Because these have spherical type of a particles, these are produced through gas atomization. And then we also said this is produced through air because there is a partial sphericity, but there is also a certain oxide layers formed. So you can see that there could be like you could have said this is a water based atomization, but it is an air based atomization. So obviously the morphology will not help us to give us a clear distinction, but we should know about the morphologies because they will help us to characterize the powders and identify the fabrication routes. So now we have some questions here. So I will read out the questions and then you can answer them. So the first question is, which is true with respect to the centrifugal atomization? First, spherical shape. Second, high productive production rate. Inexpensive and less contamination. So which is the combination true for the centrifugal atomization? Which of these combinations is right for centrifugal atomization?
First one, 1 and 4. 1 and 4.
So, in centrifugal atomization, the spherical shape of the particles are produced, which is right, and you're saying the less contamination. So, option 1 and 4 is right because the high production rates are not possible with centrifugal atomization, and it is also not inexpensive because there is a high plasma or a high energy arc used for the formation of particles in the centrifugal atomization. But yeah, it is saying there's less contamination, but you should note that there is some contamination in the centrifugal atomization also. So can anybody tell what is the contamination possible in centrifugal atomization?
Uh, from the electrode, tungsten electrode.
Yes, the electrode that is used as a, say for example, cathode, which is producing the arc, that can contaminate the powders. But yes, comparatively, it has a less contamination as compared to say water fluidization, water atomization. Okay. So now next question is, if you are tasked to produce fine, high purity spherical powders of a metal in huge quantities, which process you will use? So the question asks you to produce fine powders. It is also asking you to have them high purity, so there should not be any contamination. It is also asking them to be spherical. So and also in huge quantities. These are the parameters that it should be fine, it should have a high purity, it should be spherical, and it should be produced in high quantities. So which of these atomization is best? Is it gas atomization, centrifugal atomization, thermal decomposition, or electrolytic method? First, based on your particle shape, spherical
Gas
powder.
automation.
Okay, right. So how will you approach such problems? Is that first you take the particle shape because particle shape is very small domain because there are proper characteristics for each type of process manufacturing or fabrication of the powder process. So for example, spherical is either in gas atomization or either in centrifugal atomization, right? And then you also have to have a high purity, but because in centrifugal there was possibility of contamination, in gas there is not any possibility of contamination, so you can have a high purity product. And also because gas atomization is a high velocity driven atomization, so the fine particles can be produced if you modulate the certain parameters. And also the quantities can be produced in huge quantities because I think it is about 40 or 60 kgs per minute the powders can be produced. So there is a large quantity of powder that can be produced by gas atomization. So you have to approach these problems by one. You have to see which characteristic fits which type of processing route. Uh, the next question is, what is an embryo in the nucleation and growth of a solid? Is it unstable particle below the critical radius, unstable particle below the critical radius, stable particle above the critical radius, and unstable particle above the critical radius? This is something we talked about. What is critical radius? Is it below that or above that?
Unstable particle below critical radius.
Right, because what we are saying, we are talking about an embryo in the nucleation. So we are saying what is the starting particle of the nucleation and the growth. So it will not be a stable particle below the critical radius, because critical radius is the requirement for a nucleation to take place. Because we saw in that diagram that if the radius is less than the critical radius, then it will shrink. It will completely vanish out. So it will not be stable. The statement is wrong. The other point is the unstable particle below the critical radius. This is the right option, the unstable particle which is below the critical nucleation, below the critical radius. The next question is, which gas is suitable for gas atomization? CO2, nitrogen, oxygen, or air? Which of these gases is suitable for gas atomization? Carbon dioxide, nitrogen, oxygen, or air?
Nitrogen.
Come again. Is it
Nitrogen.
nitrogen? Okay. So the gas which is suitable for gas atomization is nitrogen. Can you tell why?
Because one is it is less costly, the economical,
Uh,
and air and oxygen may lead to oxidation also.
right, because oxygen and air will oxidize your metal stream, so that will not be suitable for gas atomization, because it will be similar to what you do in water type atomization. And nitrogen is an inert gas, and that inert gas will prevent the oxidation of your melt, and as such you can have a, like, you can go for gas atomization for like for very reactive powders. You can go for gas atomization in the presence of nitrogen, so it is a suitable method for gas atomization. The next question is, the coarse particles are obtained in water atomization as a result of, because we are talking about water atomization. Now we are saying that if in water atomization we want coarse particles, so what should be the conditions? We should have a low velocity, the low velocity of the water jet, the high velocity of the water jet, the low nozzle to metal distance, or none of the above. So what is the condition that I should keep for coarse particles in water fluidization, in water atomization, sorry?
Low velocity.
Low velocity, why?
The cooling rate.
Yes, because what happens during water atomization, the water particle, it is actually a reaction. It is like a bursting of the melt with the help of a water jet. The water jet, if the speed is very high, it will enforce a large amount of forces on your melt, and that forces will help in production of large amounts of powders which are fine in size. But if the velocity is very slow, the standard cooling rates will be slow, right? If the standard cooling rates will be very high, and that will result in formation of a coarser particle. So if you have a very high velocities, that will result in finer particles. But if you have a low velocity, that will result in a coarser particle in a water atomization. So we can optimize the particle size in the water atomization based on the velocity. While this nozzle to metal distance does not have any significant influence on the particle size. Then we have under what conditions atomization process will yield spherical particles. The longer solidification time, the shorter solidification time, both of A and B, none of the above. We need to have spherical particles. You have to think of this because the spherical morphology is having a surface energy, least surface energy. That is why the particles, whenever they solidify, they tend to take the particle shape of a sphere because it is having a least surface energy. So, for that, we need to have a spherical. We are here talking about spherical particles and having a least surface energy. So, what should be the time of solidification? For this atomization process, because we are talking about spherical particles, we should have a shorter solidification time or longer solidification time. So based on this, we can say that if we have a melt, for example, if you have a melt here, and from this melt you have to solidify a particle, and that particle is in the form of sphere. The spherical shape is the least surface energy shape because that is having a least surface like volume to surface in a ratio. So for that we want to have a spherical particle. So for giving it a sufficient time to solidify will help it to achieve the spherical position. Otherwise, if you try to solidify it quickly, it will attain a irregular type of a morphology and it will not be solidified as a sphere. So for any powder to be solidified in the sphere, you should give it enough time, and for that time you should have a longer solidification times. So for longer solidification time, the particle will slowly condense or slowly solidify in the form of a sphere to achieve a least soluble, least surface energy state. So the answer is longer solidification time. So for any spherical particles, if we want to have a atomization process to achieve a spherical particle, we should go for longer solidification times. The next question is during atomization, the sphericity of the metal powder is controlled by long flight paths, inert gas atomization, high surface tension, or all of the above. The long flight path means the path that is from the metal, like from the melt, because we have something like this. We have a melt here, and we have a melt nozzle here, and during the atomization, we have either gas or water being impinged on the melt. So the flight path is how much distance it travels before it is solidified in the chamber, right? So this is the flight path. And then the inert gas atomization is because of the inert atmosphere or the high surface tension. So you have to say that during atomization, the sphericity of the metal powder is controlled by the long flight paths, inert gas atomization, high surface tension. See, for first option, the long flight path means that you are giving it enough time in the chamber, inside the collection chamber, for it to solidify. So that long flight time is similar that you are giving it a long solidification time. So the sphericity will be maintained if you give it a long flight path, right? This is right. Then it is also controlled by inert gas atomization because we saw that if you have a gas atomization based on nitrogen or inert gases, it will tend to achieve a spherical morphology. So that is also correct. then we are talking about high surface tension, because we are talking about this sphere. It has to form, it has to have a lowest surface energy. So because of the lower surface energy, it will have high surface tensions, and that will result in the formation of a sphere. So the answer would be all of the above. Is it clear? I think we will move to the next question. The question is, in a nucleation and growth mechanism, the critical radius depends on surface energy, volumetric free energy change, growth rate, or all of the above. You have just solved a numerical on this. So you have to say that the critical radius, based on the equation that you wrote there, what is the like the critical radius depends on what of the factors? Will it depend on surface energy? It will depend on volumetric free energy change, and it will depend on growth rate, or it will depend on all of the above, based on the formula that you wrote for the numerical. Can anybody answer? Am I audible? I think there was some issue with the connection. Am I audible?
But you were lost actually.
Yes, yes. So can you tell me where exactly, what was the last question that you...
Yeah, that was nitrogen and oxygen.
Okay, so this is the... Okay, so this you did not check this, right?
Yeah.
Okay, okay, it's okay. So the question is, the coarse particles are obtained in water atomization as a result of low velocity, the low velocity of the water jet, the high velocity, the low nozzle to melt distance, or none of the above. So which of these is right? If you want to achieve a coarse particles in water atomization, what should be the condition of operation? Can anybody answer this? Any answers?
Low velocity of water.
The low velocity of the low velocity of the water jet will help us to achieve coarser particle sizes, because if you go for a very high velocity, there will be large amount of nucleation sites for in a water atomized in the melt say for example, so that large nucleation sites will result in finer particle size, while as in a low velocity there will be low nucleation sites and there will be coarser particles obtained from the atomization. The next question is, under which condition the atomization process will yield spherical particles? The longer solidification time, shorter solidification time, both A and B, and none of the above. Because we have to achieve a spherical particles.
Longer solidification time.
Yes, because if we have a longer solidification time, that will give it enough time for the sphere to form, because spherical morphology is the like lowest energy morphology, so it is a lower surface energy. So to achieve a lower surface energy morphology, if we give it sufficient time for solidification, it will achieve a spherical particle morphology. And then the next question is, during atomization, the sphericity of the metal powders is controlled by long flight paths, inert gas atomization. Atomization, the sphericity of the metal powder is controlled by long flight paths, inert gas atomization, high surface tension, or all of the above. We want to achieve a sphericity in the from the melt. Should we operate under what conditions? The long flight path. So the flight path is actually the distance inside the chamber. So for example, this is a melt and this is a melt nozzle. So it is being impinged with gas or water. So the flight path will be this distance. The distance that the particles will cover until they are solidified. So if we have a long flight path, we will have a longer solidification times. And if we have an inert gas atomization, we already know that in gas atomization we can achieve the sphericity. So this is right. The long flight path is also right. We can control it with the long flight paths. And the high surface tension, because the high surface tension is required, because high surface tension means low surface energies. So low surface energies will help us to form sphere particles more quickly. So that will be all of the above will be the answer. So next, in a nucleation and growth mechanism, the
Previous
critical,
question, what was the answer?
the answer is all of the above.
No, not previous question.
Longer solidification time. Yes. Okay. So in a nucleation and growth mechanism, the critical radius depends on. So this is the numerical that you have done. So based on that numerical only, you have to tell that the critical radius depends on what factors? A, surface energy, volume free energy, growth rate, and all of the above. So you can go back to your critical radius formula and you can check what are the factors that it is dependent on. So the critical radius formula was 2 times the surface energy raised to power 3 divided by delta G, right? That delta G was the volume free energy. So it depends on what factors. What is the right answer? Can anybody tell what is the right answer based on the critical radius formula that you used for solving the numerical?
A surface energy only, I think, in this.
Mm, see, what was the formula for your critical radius? I'll just copy it here. This was the formula for the critical radius. R critical radius was dependent on surface energy, that was this. It was also dependent on enthalpy, and it was also dependent on your melting temperature or undercooling, right? This
Yes,
this
yes.
factor is a delta G actually. This is the volume surface energy. If you go to this equation, because we knew that this R critical is equal to 2 times the surface energy into the melting temperature, right? But this delta G by delta T, you found it using this equation that it is the volume free energy, right? So you can write this critical radius also as 2 times the surface energy into the melting temperature, or you can write as 2 times the surface energy divided by the Gibbs free energy for surface change. Why? Because you wrote that this delta G is equal to delta H delta T by T melting. So you can replace this delta H, delta T and T melting by delta G in this equation. This delta H, T delta and this T melting, you can replace it with delta G, right? So you will have the R critical is equal to 2 times the surface energy divided by this delta G. So it depends. The critical radius also based on this equation, based on this graph, you saw that the critical radius will depend on two energies. One is the volume free energy change and one is the surface energy. So it will depend on both of these factors. So here in this question you have the critical radius dependency on surface energy because you are creating new surfaces during nucleation, and that will depend, the critical radius will depend on the surfaces that are created, and it will also depends on the volumetric free energy change that occurs because you are solidifying from a liquid to a solid. As you move from liquid to solid, there was a decrease in the Gibbs free energy that will result in the volumetric free energy change. But during the critical radius dependency, we do not have any dependency on the growth rate because growth rate comes after critical radius. Once you have achieved a radius greater than the critical radius, then the nucleus will try to grow into bigger particles or coarser size particles. So the critical radius will depend on surface energy and volumetric free energy. Is it clear? You just have to replace your delta G value in your critical radius equations with the give this volumetric free energy change. So the next question is, for a finer particle size in a process governed by the nucleation and growth mechanism it requires. So we are trying to have a finer particle size and we need to tell how we can achieve the finer particle size. So it will be by high nucleation rate and high growth rate, low nucleation rate and high growth rate, low nucleation rate and low growth rate, high nucleation rate and low growth rate. So what is the best combination between nucleation and growth? Because nucleation
High
is,
nucleation,
yes, what is the answer?
high nucleation and low growth.
High nucleation rate and low growth rate, right? Because for fine particle sizes we want to have a large number of nucleation sites. As there are large number of nucleation sites, there will be a finer particle size, but we do not want these large number of nucleation sites to grow or agglomerate together to form a coarser size. So we should have a low growth rate. So you will always have a lower growth rate and a higher nucleation rate for finer particle size. The next question is, at the melting point, the free energy of the liquid and solids are equal, unequal, cannot say, depends on other parameters.
Equal.
Yes, because the free energy of the liquid and the solid are equal. That is why we are trying to move towards, and as you move towards solidification, then there is a distance, there is a difference between the Gibbs free energy, either below the melting point or above the melting point, which makes solids as more favorable formats below the melting point, while liquids are favorably formed above the melting point. So at melting point, the Gibbs free energy will be, for the liquid and the solid, will be equal. So you can say, like for example, for example, if I have a graph like this, right? So I am saying this is for solids and this is for liquids, right? And this is the point where I am talking about the melting temperature, melting point, right? So what is the like which is more stable below this? So we have Gibbs free energy for a liquid is more is greater than Gibbs free energy of the solids in this region above the melting point, and below the melting point we have Gibbs free energy of the solids greater than Gibbs free energy of the liquid, and at the melting point both of these are equal. Is it clear? So, a little brief about some of the parameters of atomization. So, we learned about atomization, but there are certain factors that influence this atomization process. So, for example, we have the liquid metal superheat. So, what do you mean by liquid metal superheat? The melt that is being produced here is not having only the temperature, it's not at the temperature of its melting point, but it is at a temperature greater than its melting point because it should have some extra amount of heat in it so that it can sustain the transfer of the melt through this chamber during water or gas atomization, and it can be solidified only in the later stages after the nozzle or the jet has been impinged on it. So you should have a liquid metal superheat. So there should always be heat inside the metal which should be higher than what it would be at its melting temperature because it has to sustain the process. It has to sustain all the atomization requirements in this chamber. So also the parameter that will influence your atomization process is the viscosity of the melt. What is the viscosity of the melt will influence its process. Also because if you have some second ion species inside, for example, you have two metals or alloyed elements and you have alloyed them together in the melt, the viscosity of the two will be different. So it will influence your atomization process. So then the other process is the atomization temperature because sorry atomization pressure. So at what pressure you are impinging the molten metal will have an effect on your particle size because we saw that if you have a high velocity particle jet you will have a finer size. If you have a low velocity particle size you have a coarser particle size. And also the geometry of the nozzle. The geometry of the nozzle also influences it, what kind of an orifice it has, whether it has conical orifice, whether it has a larger orifice that will influence your particle sizes and shapes. So in general, the parameters that are operated for gas and water atomization are here. So you can see that for a water atomization, the pressure requirements are very high, right? It is about 21 megapascal, and also the velocity of the particles of the gas atomization and water atomization is like near about same, so it is run between 50 to 150 meter per second square. So we have some superheat also. For gas atomization we have 100 to 200 type of superheat, but for water atomization we have 100 to 250 like superheat. That means for a water based atomization you should have a larger superheat as compared to gas atomization. So this will cover in a while that why this is required. Also there is a difference in the angle of impingement. Like for gas atomization it can vary in a large range, but for water atomization it should be less than 30 degrees Celsius only. And also because we talked about the particle shape which are smooth and spherical for the gas, while as for water it is irregular and rough. So this is what is important to understand in the gas and water based atomization, that during atomization process what happens as the molten metal is impinged with your atomizing medium which is either water or gas. First stage formation is the wave formation and the second stage of formation is the ligament formation. So as you have this flat type particles, these are converted to ligaments in the second stage. Now in second stage you have two influencing parameters. One is if you have a low cooling rate or you have a high cooling rate. This will significantly affect your consequent particle morphology. So for example, if you have a low cooling rate, the low cooling rates will try to give it a long solidification time, and as a result the particles will form spheres as we talked about it. But if you have a high cooling rates in this process, so you will have membrane type fragments. This is a major difference that occurs in the gas and water based atomization. In gas based atomization we have a low cooling rates, and this low cooling rates helps us to form spherical particles. While as for a water atomization, because we have very high cooling rates, these high cooling rates result in the formation of irregular morphology. So based on the cooling rates, we have different types of particle morphologies and subsequently different flow characteristics. So this is important to understand that why we have a high cooling rate in say for example water atomization, while we have a low cooling rate in gas based atomization. So in gas-based atomization, we have spherical type of particles because we have a large cooling rates. We have a small cooling rates possible in gas atomization. That will result in the formation of spherical particles. While as in a water-based atomization, we have high cooling rates, and that results in formation of irregular surfaces. So this is very important to understand in context to gas and water-based atomization. And also these are some of the questions where we say that spherical shaped particles are produced by centrifugal atomization. Is it true or is it false?
True.
Under what set of conditions is the irregular, this is right, true is the right answer. Under which set of conditions is the irregular particle shape obtained? The lower surface tension and low cooling rates, higher surface tension and low cooling rates, lower surface tension and high cooling rates.
D.
It is D, lower surface tension, because it will have a it will have a irregular size, so it will have a lower surface tension. And high cooling rates, if you have high cooling rates, just like water atomization, you will have a irregular type of particles. Then which of the following depicts the stages of molten metal disintegration? Wave, ligament, powder. Wave, ligament, fine droplets break down to smaller particles and then to powders. Wave, ligament, fine droplets, and then break down to smaller particles, collision and coalescence of the particles. Or D, wave, ligament, fine droplets, and collision and coalescence of particles.
I think D here also.
Okay, the answer is C. So how we are approaching this? First, it is clear that once we have a stages of molten metal disintegration, wave is the first thing formed. That is, the flat surfaces, flaky substances are formed. Once those flaky substances are formed, they are further elongated and they form ligaments. Then they are formed fine droplets because there is a continuous impingement of the water or gas. But what happens once you have the fine droplets? Once you achieve this condition where you have a smaller particle of your powder, but you also have a smaller particle of your, say, medium, which is the gas or water. This small particle of the medium, say for example, this is a particle of the medium, and this is a particle of your melt. So this particle of your melt will again collide with this. There will be again collision between the particles, and as it will be colliding, there will be subsequent formation of finer particles. So this is also one stage of formation of the powders. So first there is a wave, ligament, and fine droplets, because that is due to the impingement of the water jet on the, say for example, water jet on your metal stream. But also once the small particles are formed, the metal particles are again impinged with the help of water particles to smaller particles, and there is collision occurring and coalescence of the particles. So this is also one stage in the metal disintegration, right? So now we have one more question. It is saying that the cooling rate in water atomization is much higher than gas atomization because the heat capacity of water is higher than gas, The heat capacity of water is lower than gas. Thermal conductivity of water is lower than gas. Flowability is higher for gas. We talked that in water atomization, we have cooling rates which are very high. Because of that, we have irregular type of morphology. But now the question is why the cooling rates are high in water atomization as compared to gas.
A.
Yeah, right. The heat capacity of water is very higher than the gas, and it results in large cooling rates. Because as the cooling rates are increased, it will result in the formation of irregular morphologies. So the option A is right. Now we have one question which says that in centrifugal atomization, the density of copper melt is 8 grams per centimeter cube. So this is the copper melt which is being formed for the powder manufacturing, right? And the electrode radius is kept at 2 centimeters. So we have an electrode radius which is kept of 2 centimeter, because in centrifugal atomization, we have a rotating disc or rotating rods. So here the copper melt is being used, and for that the electrode radius is kept as 2 centimeter. So what should be the electrode radius if particle size is decreased to half? Say for example, I am trying to achieve a particle size which is half of what it is earlier. So what should be the electrode radius? What will be its influence? We know that the particle size is given by A times the angular speed of the rotating disk in case of centrifugal atomization, and which is based on its surface energy and density of the melt and radius of the electrode. So you have to calculate what will be the effect on the electrode radius, that is R, if we are changing the diameter of the electrode radius. If we are changing the electrode radius, which is R, so what will be its effect on the particle size? Based on the formula, you can take 5 minutes and answer. So we will say in one case, which is D1, we are having, or we write the D1 by D2. That means we are having two conditions in which the diameter of the particle in case 1 and the diameter of the particle in case 2. So that will be equal to R2 by R1 raised to the power 1 by 2, right? So we are saying that the particle size is decreased to half. So we can say that D1 is equal to D2 is equal to 1 by 2 of D1, which will be two. Putting this value in the equation, 2 will be equal to R2 by R1. R1 is 2 centimeter. This will be 2 square. So we have 8 centimeter the radius of electrode. So that means if we are trying to decrease the particle size to half, if we are decreasing by the particle size, then we have to also change the electrode radius. We have to increase the electrode radius by to 8 centimeter. Is it clear? Any question? Any question? Is it clear?
Yeah, ma'am, clearly.
Okay, so I think that is it for today. If there is any other question, you can ask.
Yeah, I actually had lost the connection when you were explaining the replacement for that delta G by volumetric uh, free energy change in the first problem. Can you just once again repeat
Okay,
it?
okay, okay. So this problem, right?
Yes, yes, ma'am.
So you have this R, that is the critical radius. You are given this by 2 times the surface energy and the temperature of melt divided by the latent heat of fusion and undercooling. So you have to use like okay. So for example, you have to use for activation energy. So for activation energy, you have to replace this delta G, which was given by delta GV, which is a volumetric free energy. So you have to change it to in the form of latent heat of energy or and in the form of like undercooling. So for that we use this formula. We know that delta G based on thermodynamics. We know delta G is equal to delta H minus T delta S. So based on that we replaced it. One second. So we did this where we said that delta H is minus T delta S is equal delta G is equal to delta H minus T delta S. So this is the based on thermodynamics. So then we said delta G is equal to delta H minus T. Now we replace this entropy terms in terms of enthalpy because we know that the entropy is defined as H by T. So any value of entropy will be a factor of its enthalpy based on the temperature. So we replaced it with delta H by T. The red color is, you can see it by red color, the replacements. And then delta H is given by delta H. We have taken it as a one common product. And then we have 1 minus T here instead of this delta H which is outside. So we have put T naught. So now we have to solve this equation, which is T naught minus T divided by T naught. But we know that T naught minus T is simply the undercooling. How much we are undercooling it from its melting point. So that we can write as delta T. So T naught is delta T. And this T naught we have written it because we are considering the melting temperature here. So we have written it in the form of melting temperature. So then you can write it in this equation. So now you have 16 pi surface energy raised to power 3. The melting temperature comes from this delta G. You have to replace this delta G V. This is the volumetric Gibbs free energy with this delta H into delta T divided by Pm. So you have just replaced it. So from this equation you have now reached this equation.
Okay.
Is it clear?
Yeah, yeah, clear.
Okay, okay. So any other question?
Ma'am, whether these formulas we need to remember if you given the question.
Like you have to remember, say for example, for critical radius, you have to remember it. There's no other way for it. But if you
No,
remember,
just now that D equals to A by omega, that's simple.
like for the this type of formula, right? I don't think you need to
Yeah.
remember the complete formula, but you should like have an idea like what is the dependency of D and R. For example, the particle size and the dependency on the electrode radius. So you know it is inversely related underscore like square root of inversely related to the electrode radius. So that will help you in solving the problem. Is it clear?
Yeah. Ma'am, one this thing. Will this be PPT means for examination is there after like 2 months or something like that? So questions will be asked from this also for final.
Like not really all of it will not be asked because this is more of a doubt clearing session. So what you have given